Here we'll continue the discussion about treatment wetlands. This is part 2. Starting off with phosphorus reduction. We just finished completing the discussion in part 1 of the sizing of a wetland for BOD removal and for total nitrogen removal, both ammonium and nitrate. Here we look at phosphorus reduction first. For both free water surface wetlands and for subsurface wetlands, the formula is the same. We can calculate the area of the wetland using the formula given here, where the formula contains the influent concentration of the phosphorus and the allowable effluent concentration, C sub E, where K sub P and B are both constants that are put in there. Capital Q again is the discharge of the flow going through the wetland. The hydraulic loading rate does not need to be calculated directly in this formula. We would if we wanted to use the first formula that's given above at the top of this slide. But the hydraulic loading rate would just be the ratio of the discharge going into the wetland divided by the surface area of the wetland. That would give us units of meters per day and can be converted to centimeters per day. But that hydraulic loading rate does not have to be calculated directly in the determination of the required surface area of the wetland to get sufficient phosphorus reduction. For TSS reduction, there are two empirical formulas for calculating that for free water surface wetland and for subsurface wetland. If we know what the surface area of the wetland is, we can calculate the hydraulic loading rate by dividing the discharge into the wetland by the surface area of the wetland. And there are a number of different surface areas we could consider here. One would be the one for BOD reduction, one would be for the ammonium reduction, one would be for the nitrate reduction, one even could be for the one for the phosphorus reduction. Any one of those could be used to calculate the hydraulic loading rate, and of course you're going to get a different value of effluent concentration of TSS depending on which one you actually use. So if the TSS requirement for effluent concentration is not actually specified, we would calculate what that effluent concentration is depending on what the influent concentration C0 is and what the hydraulic loading rate is as designed from any one of the BOD reduction, ammonium reduction, nitrate reduction, phosphorus reduction. Little idea here about the settling of particles in a free water surface wetland. This is just some background information. It's not something that is actually used in the design on this page here. This the effluent concentration is just calculated based on the influent concentration, the hydraulic loading rate. Here the particle settling velocity is used to determine as to which particle size will actually settle out within the time that the water is flowing through the wetland. But this is not something that is being used directly in the design. It's some background or fundamental information for understanding more about particle settling in a wetland. The relationship between particle diameter and settling velocity is shown here, where the density of individual particles is plotted as one of the variables in determining it. And so clay size, silt size, sand size particles, we can see that the larger the particle diameter, the faster the settling velocity, and of course the more dense the particle is, the faster the particle is going to settle. For filtration of particles in a subsurface wetland, the process by which particles are removed is by either direct collision of the particle with let's say grains of the porous treatment matrix, by surface charge attraction between those grains and the particles that are being filtered, or by van der Waals forces, which are electrostatic forces that exist around the individual grains of the treatment bed, and those forces can attract suspended particles and hold them in place within the zone of an individual particle, and thereby consider it to be filtrated. Again, this is just background information. It's not actually used in the design equations that were shown before, because those were very empirical equations. Some guideline on aspect ratio for wetlands. Mentioned here that at one time in the design of wetland wastewater treatment systems, it's thought that maybe we should keep the wetlands narrow and long. The reason being that if you have them too wide, you're subject to a process of short-circuiting, that the water flowing down gradient would find plenty of preferential flow pathways that the water could flow down gradient along, and you wouldn't get very good treatment of the wastewater. However, it was found that if you have too long of a wetland, then you have excessive head losses occurring in the wetland, and you can actually get to the point where the water will overflow the banks or the berms that are holding that define the treatment wetland. That the rise in depth of flow, which represents the head loss that's occurring in the wetland, that rise becomes excessive. So one wants to veer away from that. So based on experience, the aspect ratio has been narrowed down to be length 4:1 width, and even more conservative to keep it down between 3 and 1. So in the design equation that you'll see in the examples and so forth, and in the design equations for both surface water wetlands and subsurface wetlands, you'll see that the ratio of 3:1 is referred to. The slides have these definitions for all the variables that have been explained with prior to this in the slide, so you can refer to this these two slides for that purpose. The assumptions that were given for both parts of this presentation are that there are no resource limitations, such as oxygen, organic matter, bacterial population. All those things are considered to be not limiting to the reaction process. The pH of the water does not change, it's assumed anyway. Flow occurs as plug flow reactor. All chemical constituents start with a pulse input at the inlet to the wetland. The variation of flow rate is not substantially different anywhere along the wetland from the average between the entrance and the exit points. Flow is steady, and vegetation is not adversely affected by any of the chemical constituents. And with that, I'm going to stop this presentation and go and talk about these examples.